Hi everyone, welcome to our 11th paper of the week, MDE paper of the week. For this week's paper I chose a 2003 paper. It goes along the lines of some of the stuff we read already, such as the ULF code generator. But this one is a bit more standards based, so it's more based on MOF. So I was curious about this paper. I haven't actually read this one yet. As always, I had a quick look at the connected papers graph. In fact, let's just do it. I am very pleased about this little tool. It's just so clever. Let's just do a quick connected papers. Sadly, we'll generate the graph again, but actually it's massive cached it. Very good. Yeah, as you can see here, it's a healthy paper in the sense there's a lot of citations. Bit of a cloud of a cluster of papers here. They're mostly related to project management and project management, that kind of thing. A few in Spanish as well, which is quite interesting. And so I had a quick look at the different clusters of papers you see here. Quite a few interesting ones, but nothing quite at the level of this paper itself. You see a lot of reports, technical reports and report experience reports. And this is how paper is actually one of the most interesting ones we've seen. So it's just really connected papers is just an amazing tool, really. You can get lost with it, really. But nonetheless, it shows this was an inspirational paper to a lot of things, so definitely worth a while having a look at. So let's have a quick look at the abstract then. The Meta Object Facility, or MOF, is the core component of OMG's model-driven architecture. MOF defines the meta-modeling language, which is used to define the languages which are used to model applications, just as unified modeling language. The importance of MOF will grow in the future. It's not quite accurate, unfortunately, because more and more domain-specific modeling languages will be defined as extensions or adaptations to the UML instead of being proprietary. This is the vision of MDA. They never really come to pass. This is probably worthwhile highlighting. Chap here. The importance of we read this already. So, to be really useful for software development, modeling languages need to be accompanied by software tools. In this paper, we present a MOC, which is a model compiler based on the Extensible Style Sheets Language Transformations (XSLT) standards. MOC generates implementation code for maximizing representations of MOF metamodels. We read something rather similar to this actually. I did got a few background checks to make sure we didn't read this paper on our recent batch, but pretty sure we bumped into something very similar to this. Let's have a quick look at our index. For SSLT, nothing particular coming up. XML, nothing particular either. Okay, it's one good thing about having org notes. Org mode for all the notes is very easy to check everything you've done before. So as we were saying, they are using XSLT to generate the model. So probably another point worth highlighting. The compiler front end mainly consists of generated code and creates an object representation from the XMI input file. This object representation is transformed into an eternal XML representation, which is easier to process by XSLT than the input format XMI. Now, of course, you can already see that we're not going to really take huge amounts out of this paper because it is not a very good idea to try to write the code generator from XSLT. Anyone that's tried this probably already knows that. It's just too low level. It's just very difficult. And also XMI, it's also not the best format to deal with either. But interestingly enough, we would like to support XMI, so it's nice for us to have some idea of the power of XMI. So it's still worthwhile reading the paper. The compiler backend generates implementation code by applying XSLT style sheets to the internal XML representation of the MOF model. This architecture facilitates the adaptation of generated code to specific purposes, as well as the adaptation of the compiler to other MOF-based modeling languages. Therefore, we think that MOC can serve as the basis for automating model transformations within MDE processes. Now, of course, we're going to vehemently disagree with this, but it's with the benefit of experience. I mean, this is 2003. It's probably simpler world. So, model-driven software development has numerous advantages over manually developed software. The most important are high level of abstraction, facilitated maintainability, less erroneous code, and higher reusability. Actually, one thing we probably want to do is just a quick note here. Well, see. Authors put forward an approach that uses XMI as input and parses it into XML, and then uses XSLT to convert so XSLT and style sheets to convert. I don't quite know if there's a typo or just to convert the XML into source code. From experience, we know this is not a scalable approach, and it's too low level. That's probably enough, I guess, just to get us going. So as we were saying, we're talking about the most important characteristics of model-driven engineering. Higher level of abstraction, facilitated maintainability, less erroneous code, and higher reusability. Always worthwhile highlighting this kind of stuff. Of course, we already have a whole lot of investigation on this. These claims are very, very difficult to substantiate, so the higher level of abstraction allows the developer to concentrate on the important parts of the system and to leave the details to a compiler. This increases productivity because the developer does not need to deal with all the details, creates consistent implementation of designs, and facilitates to deploy one design to several implementation technologies and or platforms. Now, this is a little bit naive, I guess, but remember that we're in 2003, so the advantages of modeling language compared to programming languages are the same as the advantages of high-level programming languages compared to assembly languages. Very big claim. Therefore, the availability of compilers for modeling languages would lead to the replacement of high-level programming languages by modeling languages, similar to the replacement of assembly languages by high-level programming languages. Again, this is sort of a very common attitude that we used to have in 2003. For these reasons, more and more areas of software development are currently switching from traditional to model-driven approaches. Therefore, Object Management Group developed the model-driven architecture to define an optimized approach to software development based on models. Each phase within the software development process generates additional informations which need to be added to the model by a suitable transformation. Well, this is not entirely wrong, so let's just highlight this bit here. We don't really particularly care about phases, but these transformations should be supported by tools in order to facilitate process execution and increase the accuracy of the transformations. In this paper, present MOMO, the MOMO compiler, MOMO-C, which is a model compiler based on OMG and W3C standards. It's worth highlighting. MOMO-C generates implementation code from the XMI representation of models which conform to MOF 2.0. In the following sections, we provide an overview of the architecture of MOMO-C. Alright, so let's just finish highlighting over here. Section 2 and show the steps which are carried out during the compilation process. Finally, we summarize the results and provide an outlook within MOF. One thing that is very interesting is model compiler. So authors reference model compilers and mention and reference OMG, but do not provide a definition of a model compiler. Okay. So the Momo compiler then. MOF consists of a front end which generates the internal representation and a back end which generates the implementation code. The front end mainly consists of generated Java classes which implement an XMI reader and a repository for MOF-compliant metamodels. The generated code is responsible for reading an XMI file and building an object representation of its content. Okay. The generated code. The code is generated by MOF itself and is possible to generate the front end from any other MOF-compliant modeling language, which greatly reduces the cost for adapting MOF to these modeling languages. So that's very clever, I guess. A green one on that. So worthwhile probably putting MOF architecture. Front end uses XMI. Front end is generated code that reads MOF models in XMI. Supports targeting generation to other representations that show a representation that are MOF compliant. Backend. So what do we say about the backend? Generate the code is responsible and building an object representation with its content. The code is generated by MOF itself. Okay, we haven't quite got to the backend yet. So the object representation created by the parser can be modified by user-defined modules. Currently, Momo compiler implementation contains modules for resolving naming conflicts and mapping types. So this is probably the middle end. Middle end is supplemented by user-defined modules. Present has type mapping and naming resolution modules. Naming conflicts are resolved by adding a number to the file. Oh, it's not ideal, is it? Naming conflicts are resolved by adding a number to the end of the conflicting names. Type mapping is a very sort of naive approach, really. The type mapping is needed to map the MOF model to. We did put type mapping, did we? Yes, we did. The type mapping is needed to map MOF model to an implementation technology. Now, this is the need that everyone has. I mean, of course, we had a similar need in Dogen. So you have two modes of operation for Dogen, and let's just do a little detour here. You could use native types in Dogen, which is what we do most of the time. So for example, here I'm just referencing types that are coming from a PDM, which is a standard implementation of C++ standard library, and there is no mapping going on here. I just need to make sure that this references to a valid module. And also there is the possibility to use the LAM types. LAM are language agnostic model types. We don't really use that too much. I mean, this functionality we built because originally we needed this for a specific use case. Now that use case doesn't really exist anymore. So LAM is, I wouldn't say deprecated, but it's not very used. So if I take, say, one of our test models here and look at the LAM model, should exist here somewhere. And here in the LAM model, you see I'm using LAM types, so text, character, core, byte, and so on. These types here are mapped via a mapping layer, which is provided by MASD, and that mapping layer here tells you to what the types map. So, for example, oh, actually, the mapping is done in reverse. So what you do is you'd look at, say, the C# model, the PDM for C#, and you would have a mapping to this object, as all these other types would. So that's how we do mapping in Dogen. Our mapping layer works. So returning back to our paper, the type mapping is needed to map MOF model to an implementation technology, as we explained out. That's done in Dogen. This is especially needed for models which contain their own data type definitions, which needed to be mapped to MOF or target language data types. The modified object representation is transformed to XML documents in order to be able to use the extensible style sheet language transformations, which is just XSLT, to generate the implementation code. Alright, this is still part of the middle-end, presumably. This is the only input language specific part of within Momo, C, and is planned to be replaced by a generic XML generator in future versions. Okay. Using XSLT for the transformation has several advantages. XSLT is a standard, it is well documented, and many implementations are available. The basics are easy to learn, and therefore simple changes to adapt the backend to a specific use case are straightforward. Of course, this is all nice and good if you have a very simple setup, but if you had something really complicated, then the style sheets would have become very complicated very quickly. On the other hand, XSLT is powerful enough to be used for complex code generation tasks. So, XSLT middle end transforms types into XML. So backend is made up of XSLT that generates the implementation code. Okay. It is even possible, on the other hand, XSLT is powerful enough to be used for complex code generation tasks, where we disagree with the author. It is even possible to mitigate the performance loss compared to backends which are written in a programming language by compiling the XSLT style sheet to Java. An optional formatting step finalizes the compilation process. This step is included because the output of the XSLT transformation is in many cases badly formatted and therefore difficult to read and debug. This is yet another problem. Thus, the code formatters only exist to facilitate backend development. On implementation level, the Momo compiler consists of 4 main building blocks, which are corresponding to the compilation steps we just described. The blocks are represented by the UML package parsers, modules, generators, and formatters. In figure 1, the 5th package, MomoC, contains the driver program, which controls the generation process. Okay, so perhaps this is worthwhile highlighting. This is just a complete architecture. The parsers package mainly contains the generated code to read XMI documents and build an object representation of the MOF model. Currently, the generated code is compatible with the code for the NS UML library, which is the basis for the Argo UML modeling tool. The compatibility facilitates building of modeling tools for MOF or UML profiles using Argo UML as the basis for the user interface implementation. Therefore, the backend for the NS UML compatible libraries was developed first, and the Momo compiler was initially built using the code for its internal model representation. It is planned to switch to a generated JMI implementation when JMI is available for MOF 2.0. Besides the generated parser, the parsers package contains handwritten parsers for MOF 1.4 and UML 1.5. which were used to bootstrap the compiler and are currently used to import models from UML tools as long as no MOF modeling tool is available. The handwritten parsers were originally implemented for MOF 1.4 and are now implementing the rules for transforming MOF 1.4 to MOF 2.0, which are specified in chapter 11. Let's have a quick look at the one. MOF 2.0, okay, this is just basically the MOF standard, that's fine. The user-defined modules are located in the modules package. All modules implement the predefined interface MOC module, and their code is executed before the XML generation process starts. The MOC standard implementation contains the data type mapping module, which allows to map the data types of the model to data types of the target language. The generators package contains two generators. The XML generator transforms the modified object representation to the internal representation XML. The internal representation is used as the basis for the code generation by the code generator afterwards. So this is basically our model used for generation. It's equivalent to our logical model. The main difference between the XMI and internal representations is that XMI in most cases contains the XML representations of several model elements, while our internal representation contains one XML document per model element. Right, interesting. This allows a more efficient code generation process because in most cases the implementation code is generated for a single model element and not for the whole model. An example for an implementation which contains code per model element is JMI. Now, let's just stop here for a second. If you think of something like MVC, it's a very, very similar problem to what happens in MVC. So just to recap, imagine you have a model view controller startup application. You have a view, and then you have some kind of internal representation that's actually more suitable for the domain logic. So sometimes you may have very, very complex domain logic that requires a lot of infrastructure that is not required to be presented in a view. And that's what tends to happen to code generation. The representation that you have, it's only that in reverse. So the representation that you tend to have for the domain of code generation tends to be insufficient for the output that you want to present. In other words, you've got all the information there, but it's just in a shape that's not right to make your templates really, really straightforward. So if you take that representation, you end up doing a lot of work in the templates to get things to come out right. So what you really want to do is you want to go to a set of steps, of transformation steps, to get this initial representation as close as possible to the thing that your templates want, so that it comes out really, really simple. You don't really want very complicated templates. I mean, if you look at, say, just look as an example, let's just jump over here to our stitch work. Oh, sorry, not quite that. If I could press the right buttons, it would be really helpful. So this is a classic template that we have in Dogen, and this is what you end up doing when you're developing logicless, well, not logicless, but logic-full templates. So a logicless template is just a mustache template like this guy here, which is very, very simple. A logic-full template is more like T4, which is what we use, a variation of T4. And these templates then end up having a lot of ifs and buts. So we have a class, then you need to create a final keyword text. So this is already a bad thing. Your domain model should already have a final keyword in it. It shouldn't be up to your formatting layer to now be asking for things like final keywords. And same thing for a lot of the stuff you see here. You want it to be as close as possible as the output that you're really looking for. You don't really want to have a lot of ifs and buts in the templates, because as you can see, even a very simple template like this one can become quite long. And this is just a class header definition. So what you really want is for the domain model to be very close to the view, and that's one of the reasons why using XSLT is not ideal, and starting with XMI is not ideal as your output, as a view, if you see what I mean. But this is how things used to be back in those days. The mapping from the object representation to the internal XML representation is straightforward. Each model element is mapped to an XML document which contains a root node with the name of the model element. Each reference is mapped to an XML node with the same name of the reference object which contains the reference. In section 3 we show an example for the mapping of object representation to XML representation. Additionally, to the mapping of single objects, a document for the model is created. The document contains reference to the root level objects of the model. Okay, so this is the representation of the model itself. The code generator applies XSLT style sheets to the XML document to generate code in the target language. The code generator is configurable to apply any number of style sheets to documents containing specific model elements. For example, in JMI, for each class in a MOF model, an interface of the class and a proxy which serves as a factory for instantiating the class is generated. So this is equivalent roughly to our physical model, right? The projection to the physical model. To achieve this generation with the MOMO compiler, two style sheets needs to be applied to all documents which contain information about classes. Therefore, it is possible to configure the system in a way that it searches about all documents which represent classes and apply a set of style sheets to these documents. In other words, if you were to model this to Dogen terms, what you've done is you've taken a logical projection and a logical representation, and you're trying to project that from the logical space or the logical domain to the physical domain, and that projection then results in a number of representations at the physical domain level. Therefore, it's possible to configure the system in a way that it searches for all documents which represent classes and apply a set of style sheets to these documents. So there we are, parsing, adapting, generating, and then generating to. So it generates first an XML representation, and then it's clever the way that they've done a generator for XML and then a generator from XML to code, though of course this is not very scalable. The code formatters for the different target languages are located in the formatters package. Currently the package only contains formatters for XML, DTDs, and Java. One thing we haven't actually done in Dogen yet is to support XML, something we may do in the future. Any Momo C formatter implements the predefined code formatter interface. Additional formatters for other target languages which also implement this interface are pluggable into Momo C. Compilation steps. In the following we show a small example from MOF 1.4 specification which shows the steps of the generation process carried out by the Momo C compiler. The processing starts with an XMI file which contains the representation of the MOF 1.4 meta model. We will concentrate on the classifier class within the MOF 1.4 meta model to show the results of the compilation steps. Figure 3 shows the representation of the meta class classifier from MOF 1.4 specification in the internal XML format. The document contains a root node class, slight typo there, which contains subnodes for the properties of the class. The superclass's node contains subnodes that reference each inherited class. By two attributes is parent and is inherited, the directly inherited classes are separated from the classes which are indirectly inherited. This facilitates the mapping of multiple inheritance of MOF 2.0 to programming languages which only provide single inheritance. Now let's have a quick look what's going on here. So we have an XML document that contains XMI. XMI is representing MOF. It would be nice to find an XSD for MOF actually, which is something we never did. The classifier is here. So now we have to bear in mind that this is actually a MOF representation, or an XMI representation of MOF. So in other words, this is sort of very complex what's going on here. But the meta class is a classifier inside of MOF. What we're trying to do is to co-generate MOF in effect. The internal representation is transformed into code in the target language by applying style sheets. Now this is going to be the complexity of XSLT. Figure 4 shows a cutout from the style sheet which transforms class representations into NSUML compatible Java interfaces. It is shown that XSLT templates are used to generate implementation code. The content of the templates is Java code mixed with XSLT processing instructions. So just like we use Stitch, they use XSLT to do their logic full templating. The Java code defines a template which is specific for a certain type of modeling element. XSLT code is responsible for filling in the parts which are specific for each instance of the modeling element type. So this is going to really resemble the stuff that I showed you a second ago in terms of Stitch. See here, for example, the class name, how it's obtained, and so on. The difference, of course, is instead of having the full power of C++ like we have in Stitch, they are limited to the constructs that XSLT gives them. And as we now know, it's actually, there's a lot, even very simple templates still require quite a lot of logic, and that's where XSLT kind of seems to fail a bit. The result of applying the style sheets from Figure 4 to the XML document shown in Figure 3 is shown in Figure 5. It can be seen that the name of the class prefixed by an M is used as the interface name, and that the type and that the XSL for each loop has added a superclass to the extends list in the interface definition. So you can see here it's now an M classifier, extends, this is now generating MOF. And for each would be stacked somewhere around here. Then you can see ifs and whens, and all these things are quite not easy to parse in XSLT. This paper describes the Momo compiler, a flexible tool to generate implementations for meta-model definitions. In its default configuration, the tool conforms to the MOF-2.0 standard, but it is extensible to support other languages as well. In order to be flexible, the compilation process is done in 4 steps. The first step, generating an object representation from the XML input file, is implemented by generated code. Excuse me. This code can be generated for any MOF 2.0 compliant meta model, which makes Momo C easily adaptable to other modeling languages. In the second step, the object representation can be modified by user-defined modules in order to implement specific tasks such as mapping model data types to data types of the target programming language. Within the third step, an internal XML representation is created from the object representation. Processing these XML representation is easier and more effective than processing the original XMI representation, because it contains several small files which represent single model elements instead of one package, one large representing the whole model. The final step within, well, let's stop there for a second. And this is exactly what I was saying a second ago. This problematic is the impedance mismatch between the view representation versus the controller representation or the internal domain representation. Now, if they were to make a really complex generator that took into account many different use cases, this problem will be magnified by many times. If you're just creating something as simple as a class interface, you would experience a bit of this impedance mismatch. By the time you're creating something that enables you to represent a wealth of output formats, you would have many problems, and the complexity would be much higher. So they just experienced the tip of the iceberg of this problem, and that's why they think that converting from XMI to an XML representation is sufficient. The final step within the compilation process generates code from the XML representation by applying XSLT style sheets. Our experiences with XSLT as a template language for code generation are ambivalent, so clearly this is where they're going to talk about the problems. The advantages in regard to other template languages are better documentation and tool support. The main disadvantage is the verbosity of XSLT, which tends to lead to large and complex style sheets. Additionally, the current version of 1.0 of XSLT is missing some text manipulation features, which are often used while generated code. Currently, we add these missing features by callbacks to Java code, and version 2.0 will include necessary functions. So this is clearly the beginning of the warnings that I explained. We meant to highlight this bit here, and it probably would be sensible to make this red. I mean, of course, in modern terms, no one really does this anymore, so it doesn't really, it's not something we need to highlight. In the future, we will work in the following topics: support for the design of MOF models based on Argo, UML, and or Eclipse. Increase the usability of MOMO-C by providing user interfaces for configuration backend developments. And that is it. So this was a very short paper. As you can see from our notes, we didn't really take huge amounts from the paper. It was fairly obvious from the abstract that the main interest that we had in this paper was really to learn more about XMI. And to be fair, it was a bit frustrated because they didn't really talk too much about XMI. They just spoke a little bit about XMI. And XMI here is just used as a payload for MOF. I think we won't be able to include XMI as one of our injectors because it's probably not trivial to do this, and it's not really a requirement for our initial stage of our thesis, I don't think. We will try to do something really simple like the EMF for CPP stuff that we've already spoke about in previous papers, but a proper XMI-based importer is probably beyond the scope of the thesis. And this paper didn't really help. But that's not to say this is not a good paper. I mean, you have to take into account this is a 2003 paper, and this is where much of what the landscape that exists now didn't exist. So a lot of things we take for granted didn't exist. So of course you have to put your hat of 2003 on to be able to appreciate sort of the effort of the paper. And in that sense, it's obviously a very, very clever paper, and it's just a little bit far back to give us what we were looking for. Okay, so hopefully we'll see each other in the next paper.